Okay, thanks everybody for coming along, and thanks to everybody who's online this evening. We've got a bit of a double bill actually tonight. The advertised item was we'll talk first is Trina Olsen, who's from Aarhus University in Denmark, and Trina is a PhD researcher who's doing some work in wave energy, and particularly looking at how to drive the costs down in wave energy. I'll obviously let her explain her presentation. And then we've got a second presentation, got a visitor from the Orkney Islands who's in Orkney to find out about the history of testing wave and tidal energy in Orkney and find out more about how communities can benefit from that activity. So double header, so getting good value for ORF membership tonight, but if I can hand over to Trina, who I should have said who's been here in an internship for about 3 months, 4 months, I think, to get an Orkney perspective on the issue that she's studying in a PhD. So Trina, if you could take the floor.
Hello. Yes, I'm Trina from Aarhus University, PhD student. And tonight I have the pleasure to give a talk to you about my research topic. I called it Finding a Pathway to Competitive Wave Energy Converters. So yeah, I'm a PhD student from Aarhus University. Have a Master of Science and Engineering and Technology-based Business Development. So really, I'm working in the field within both technologies and how to make money. So my PhD project is called Techno-Economic Performance Assessment and Development of an Optimization Framework for the Crestwing WEC design. And the project is part of another project that is funded by the Danish Independent Research Fund. And it's a collaboration between Aarhus University and Technical University of Denmark and an enterprise, the enterprise called Crestwing Limited, who has this wave energy converter design. They invented this particular design. So there are some challenges in the energy system today. There is a growing demand for electricity specifically in the world, and it is estimated that the demand will double within the next 25 years. Mainly due to higher demand from Asian countries, and also a growing data center industry. So that takes a lot of energy. We have the climate changes that are caused by fossil fuels, and it's threatening the environment for people and for their livestock and the nature as a whole. And also there is geopolitical instability, and I don't know if you guys can recognize that picture, but it was, yeah, Sandy.
Guessing something to do with how the sea pipeline or something.
Yeah, the ripping of the Nord Stream gas line. Yeah. So we are up against some challenges. So there is a there is a need to make the energy system more resilient, and it's been going on for some time already. So from the old paradigm that was based on big centralized fossil-based plants that produced energy and sent it out on the net, to more decentralized and renewable bi-directional system that has a lot of smaller production plants that is integrated into local communities, and they are placed in the remote areas, and that is paving, or you would say that is a way to make more energy and also to make the system more resilient against disruptions like cut of gas lines or cut of whatever. And also there is, it's also based on renewables for most of it. So it's also addressing that fossil fuel problem that's still is, but it's in some places in the world the amount of fossil fuels has diminished. But still, there is a problem with the renewable energy. Many of the sources are intermittent. This is a recent picture from the Danish TSO Energinet that shows the energy demand up here, the orange line, and then we have the wind energy production, the tall green ones, and solar. In November, it's the yellow ones that are not so big, but they're measurable. And then also the dark green in the bottom is it's biomass. So there is a gap between the demand and the actual production of renewables. So that's a problem that has to be addressed. And how can we close those gaps? Because the wind is not blowing all the time, sun is not shining all the time. So there are different measures that can be taken to close these gaps and balance the supply against the demand is one of them. Adjusting when you use the energy, that is, I don't know how much in up here it's been going on, but in Denmark they have been talking about doing your laundry at night or whatever when the energy is abundant. Energy storage is one thing, and also alternative resources. There are still some around, because oceans contain a lot of energy, but can we use the ocean's waves to close these gaps? This picture looks quite ordered. It's like there's a plenty supply of energy coming in there. And also, yeah, the wave energy resources in the world are quite large, a huge global potential that actually would be able to sort of meet the growing demand towards 2050. So there's a lot of wave energy out there, and it's the best sites for locating wave energy is around 30 to 60 degrees latitude, north and south. That's where the waves get big because of the weather. And they're actually in out in the Indian Ocean here, South Indian Ocean. There's a huge potential. It's actually compared to up in the North Sea. There are also quite good potentials up here around this place, around 20 to 40 kilowatts per meter. And compared to the wind, it's quite concentrated, and that's because of the density of the seawater compared to air. So there's quite a lot of kilowatts. And why should we use wave energy? Yeah, it's actually, if you can see this animation, it's the colored areas are the isobars. So that's the wind, and the arrows is the wave direction. And I don't know if it's super clear to you, but it's like the wave comes and then the wind comes and in, and then the waves adjust to the direction of the wind, and they stay there for a bit of a while because the waves are heavy. So the waves are slightly phase shifted to the wind, which means that they are around when the wind is not there. They are also available at night and during overcasts, and they can be forecasted relatively accurately, which is good for renewable energy source. So there's been a lot of development in different directions within wave energy, and this is just a minor fraction of the design types that are around. There are static types that utilize water pressure or wave pressure, where the wave forces is forced down through a turbine due to a gradient, height gradient, or it can be like this one here. It's an oscillating water column, so it pushes the air on top of the water column, and that pushes through an air turbine, so creates energy that way. And then there are some dynamic types of oscillating bodies, as they're called, which are more they're dynamic. They move. The body of the device moves. Either it has a reaction point at the bottom of the sea, so it sets on the sea and then it moves. This one is it goes with the surge of the wave, so it's like an oyster. These down here are point absorbers, so they have a mooring, an anchor in the bottom, and then they heave and down with the waves. These two designs are dedicated to shallower water near the shoreline, whereas a device like this one it has a moving body inside. It's like gyrostatic device. And then there is this type up here, the raft type, which is dedicated for real offshore conditions where the weather or the wave conditions are really energetic. And this is how it works. Makes sort of a pitching movement on the waves. So it doesn't react against the seafloor, it reacts against itself. And that makes it suitable to go out far in the ocean where there are really big waves. And it also means that there is a potential to build these devices at the utility scale capacity, because they're really not like a size maximum for them, rather than only in terms of the materials that they're made of. So some of these designs are made quite big, and this up here is the device that I know of, the crest wing device, and this down here was it's the Pelamis that some of you might remember from sea trials of Orkney up at Ilia Crew, and it's decommissioned nowadays, but it's a very well-known example from the wave energy research. But yeah, of course, there are some challenges, because the ocean's swells do not always come in like ordered waves. Sometimes the weather gets rough, and the wave pattern is all chaotic. Sometimes there are no waves at all. So that is also a problem, you could say, for availability, because yeah, if it's like when the wind doesn't blow and the windmills are not producing anything. And also a challenge is the cost, because it's different from wind energy. Wave energy is not developed on land, or it's developed in wave pools, but really to really test the technology, you have to go out to sea, and that's the problem. You cannot just drive around with your truck and look after it. It sits in an area that is not so easy to access. So and also for the constructions, they need to be sturdy, they need to be robust to withstand the environment. So the focus of my PhD project is to see how can we increase the techno-economic performance of this raft type wave energy converter. And to do so, I'm looking into what techno-economic aspects apply to this specific family of wave energy converter designs, and how can the efficiency of a wake design be validated, because you also need to make sure that whatever we develop is actually true, and can be transferred to real life situations. Also, there is the economic aspects of the components, the materials that the wave energy converter is made of. So it's also has an impact on the efficiency, um, the, economic efficiency. And lastly, the big end goal for this research is to see how I can develop a framework that can help improve this performance of the raft wake technology, make it more, let's say, more competitive in the long run, but also to be able to pinpoint where in the development process is do we need to focus on at a given time. So the Crestwing design is it's serving as a case study for my research. And this is the Tordenskjold prototype that is 30 meters by 7.5 meters in size, and it has been out in marine tests in Kattegat, the water that divides Denmark and Sweden. The waves are not as energetic there as they are in the North Sea, so that's not for utility scale production of energy. What we want to is to size it up to about a megawatt size, but that's challenging, and we can't just build a bigger device because it's very expensive, and the company behind is a little one. They're startups, you could say. They're a very small company. So in this project, the Danish Technical University is using simulations for a scaled-up device, and then I will be using a techno-economic indicator. And this now it shouldn't be too technical at this talk, but I'm using the levelized cost of energy. I'm using it as it is a measure of the lifetime costs divided by the lifetime energy production. So that gives us an idea of what is the price of a megawatt hour produced by this device. Normally, the levelized cost of energy is used as a parameter for benchmarking different technologies against each other. It's not the way I'm going to use it. It's more like an indicator for the stage of the development of the device itself. So we could say I'm comparing it to itself. So there are simply there are three main elements of the levelized cost of energy. There are the capital expenditure and the operations and maintenance costs, and then there is the energy production. And also there are the raft wake system contains 5 subsystems, which is the outer structure, the whole, the device. It has a power takeoff system that takes up the energy that is absorbed by the structure. It has moorings to keep it in place and to make sure that it doesn't disappear. Control systems that that can be that there are different control systems, but there are some systems that control the power takeoff, the damping of the power takeoff. So it has some resistance, and there are also all electronics and computational controls, sensor data collection, and so on. So the control system is also made of many subsystems. And then there is a transmission system, transmitting the energy produced away from the device to a connection point, either the main grid or whatever other takeoff there might be offshore for other purposes. So I divided my work package or divided my study into 4 work packages, and for as a start, establishing the knowledge of wave of a raft wake technology. Next, validating the performance, so analyzing the energy production of a full-scale device, and see how that's what profile it has, like production wise, and addressing the scaling gaps. So in work package 3 here, I'm going to break down the costs and assess what challenges there is for scaling the device up. And finally, the development of a framework that can be used for making the device more techno-economically efficient. So I have some results from work package 1, which are preliminary. It's a scoping review, and I've been searching the databases, and I'm right now at almost 60 sources that I've selected for review. And in these sources, I can see that there is a lot of studies that focus on simulation, and there are not as many experimental data around. Some of these, if you will see that if you add these numbers together, it's not 59. It's a little bit more, and that's because some of the studies both include simulation and experience. And then there are some economic analysis, not so many. For the topics covered, many of the studies are working with the hydrodynamic efficiency and the power takeoff. And then a minor part of the studies focusing on moorings and controls and transmission. I should say that by controls here, it's more the computational controls rather than, or here there are also controls, but they're more focused on controlling the power takeoff. So these are very much connected, these 2 kinds of topics. But there are some recurring themes that I've seen. Simulation for hydrodynamic efficiency is still being researched, and you could say that this kind of a picture of where in the development phase is this technology, because we're still at the basics. We're still at the finding out how efficient the devices are at taking up energy from the ocean. But the further steps ahead towards actually producing and sending off electricity, it's not so much. There are also validation of these predominantly numerical models that are being developed against experimental data. So there is some validation going on to secure that the numeric models are you say they're realistic. So quite a few studies are focused on advancing the simulation to make it more realistic and to take into account non-linear effects that might be that you see in the real world. Damping control of the power takeoff. So how much resistance should be put on the interaction point between the rafts. And also there are some studies that also go into seeing how to utilize other physical effects. And then there are few economic analysis around that is more or less they are in general they are based on very few realistic or very few real data that are often quite old, but it's all there is. So they're building on top of this. Actually, from the beginning I thought that I was going to do a meta-analysis, to make a statistic analysis of the levelized cost of energy here, but everything seems to come down to the Pelamis device. That was one of the very few that actually went to sea and that brought data to the world. So it's still a lot of assumptions and bold assumptions are taken when we look into the economic side of the technology, which is there is a gap here. There's a gap between the different sides of the research in the field. But what I also can see is that there are some, let's say, characteristic interdependencies in the raft WEC system. One is to create high enough torque to produce a force for the generator with quite small angles because of the wave crests. It's not producing super big angles. So there are quite some high requirements for the power takeoffs and the gearing of the devices. Also, is very typical for raft wake design is that it has some of some of these designs are quite efficient at their resonance point. So they have a peak where they really are really effective, and that's when the length of the raft is about half the wavelength, because then it fits over the wave crest. But outside that wavelength, it's not super efficient. So they have this you'd say this drawback that they need to have very specific conditions in order to be efficient. And that's really also a problem, because if you develop the devices for being super efficient, and and you can make the configuration of the structure very specific for this kind of condition, but when it goes out in the real world, it's not the case. It doesn't have like the waves. The waves out there are not the same all the time. So that's it has an interdependence with the wavelength. Structure, the size of the structure, and the amount of energy that it can absorb is also depending on each other. The bigger the structure, the more powerful the power takeoff should be in order to take all that energy that is actually absorbed into the structure. So there is a relationship between the actual size and the power takeoff, the capacity that should be put into the device. Hybrid controls are or hybrid controls. Yeah, I should explain that there are different types of controls. There are passive controls that are actually not doing much. There are mechanical controls that puts a resistance on the power takeoff, and then there are active controls. There are computer control, like they're using algorithms to forecast the next wave, so they can adjust the resistance over the power takeoff and make the device absorb the energy better, so make it more efficient. And that is a way that you could say to tune the structure so that it might not need to be as big as if it didn't have the active or hybrid controls, because it's more efficient as it is. And really, the reason why we might want to make a smaller design is that the capital costs are really big for this type of technology. So the smaller you can make the device, the better economically. Then also special for the raft wake is that it needs a horizontal freedom of movement, so that it can adjust itself to the wave direction. if it doesn't have that, it will not be as efficient in order to take up the energy. So what is important is that there is not much load on the mooring lines. They should be flexible in order to let the device yaw. Is it called yawing with the wave direction? And this picture here is actually the crest wing. It has like 3 mooring lines that are they have some elasticity. These here they're like adjusting the elasticity, and then it has a turret sitting in the device in the front, so it can turn 360 degrees in the horizontal plane. So whenever the current, so the wave direction shifts, it can turn naturally and adjust itself naturally in an optimal position to the wave direction. And yeah, there are also some trade-offs that I've come across. Is that the active controls, the computer managed controls, they are able to boost the energy absorption in the structure, but they are also creating a complexity to the system. So the more electronics you put into the device, the more fragile it is to the elements, and also stress loads on the device, since it is tuned to absorb more energy than it would without having this forecast of the next wave, where you can adjust the right damping. So it simply has it's more force on the components and the structure. And also it might also underperform in real conditions, because some of the algorithms might not be able to respond well enough to real conditions where there are a lot of different types of waves coming in. Scaling, on the one hand, there is economies of scale. The bigger and more devices, the more energy that you can produce, but also it puts it increases the unit costs, and increases the risk of anything happening during transport that is going to be expensive, and also as well the maintenance. Also, simply the fact that when you make a big device, it has to go further out to sea, which means that when you have to maintain it, you need a ship to go far out, and you need the right weather conditions to go up. So that also is a con, you would say, to in order to make it more techno-economic. Elasticity of the mooring lines. They, with the elastic moorings, you get smoother loads on the construction, and it's also for the survivability of the device, that it doesn't get pulled underwater in rough weather. but yeah, again, like as I said before, it's might challenge the algorithms that are not geared to cope with these conditions. And I can see the time is flying, so really, I'm not. These are the next 3 slides are more or less summing up what I've just said. Well, the what makes the capex higher is like upscaling, adding complexity, bespoke design. It's of course more expensive than using standard components and simple layouts and modular designs. Active controls on the one hand, it's a more advanced type of control that is more prone to failure because it's complex. On the other hand, it's it could be that it provides or it makes it possible to make smaller structures. Also for capital drivers, yeah, I haven't talked so much about the transmission system, and there is really not much research into that, but co-location with other activities at sea might be a possibility that could drive the capex down, because you don't have to put sea cables all the way to shore. Operational cost drivers, again, upscaling and higher torque requirements and active controls. Longer distance makes operational costs grow, while using things that are already around, modular designs, standard components, it's driving the OPEX down. Robustness, so the device is more sturdy and can withstand the environments out to sea. Freedom of movement, again, also something that is connected to the survivability and robustness of the system, or resilience of the system. Flexible moorings, co-location, if you can share the costs of the cables with other economic activities that goes on, like drilling platforms or wind turbines, if that's possible to co-locate with, which is those passive controls, which are just also enhancing the survivability of the device. They're not like adding so much to, they're not tuning the device for better absorption, but they're made so that the device is, for example, shut down during extreme weather, and it has end stops. That's so you could imagine that if a big wave comes and it's actually sort of knocking off the gears from the push rod. So that would be the end of the device. But the passive controls can be like end stops, so you don't get into those situations where the device is destroyed. Yeah, energy production drivers, again, upscaling, making bigger devices also provides the opportunity to harvest more energy from them, having a good resonance with the wave to raft length. The size of raft length and wavelength is connected, and the better they fit, the more effective. Enhancing the PCO efficiency. Active controls to boost the uptake of energy, and passive controls to make the device survive. And actually, the hybrid controls are a mix of passive and active controls. That has actually some studies have shown that they by using hybrid controls, you can actually get a better energy absorption that with either alone. So there is a synergy, a synergy effect by combining them. Again, freedom of movement, so that the device positions itself optimally. Whereas, again, passive controls might be too conservative, so you lose some of the energy that you might have been able to harvest from the sea. Bearing losses in construction is also something that is significant for the lifetime energy output. And then also, how well does this construction itself take up the energy from the ocean? Does it absorb it efficiently, or is some of it just reflected back? So it has to be hydrodynamically efficient, so that the weight just doesn't disappear. For the coming, or I should say, this is what I've seen so far in the literature review that I'm looking into. So the next 3 work packages, the next step is in collaboration with the Technical University of Denmark to look into how can we validate the performance of the crest wing design. And to do so, we are looking into sites in the North Sea where there are some drilling platforms, and it seems that the wave conditions there on average suits a size that is a scale that is 80 meters by 40 meters. So that's still, you could say, within scale that can be produced at a normal shipyard. So it's not an impossible size, and also using or aiming for delivering energy to drilling platforms, also amidst the challenge of having a sea cable going all the way back to 250 kilometers to a connection point in Jutland. If it can be used offshore, and we know that these drilling platforms, they use diesel for generating power, so that might be an opportunity for the technology to come into the market or to deliver actual energy. So we're looking into that, and I've selected a list of 20 different sites, but we'll pick out some of them, 4 or 5 sites in the North Sea, and then we'll make simulations. So based on mid-ocean data for wave heights and specifically wavelengths, we can make a simulation of how would this 80-meter device then perform at a given place. So out of this, there will be like an energy, say a scatter plot for how much energy could this device produce on an annual basis. And then when we have these different sites, we can make a statistical analysis to see how does this technology actually produce across these locations. Where would it make better sense to put it out, or is there too much difference between the sites, or does it actually have a fairly equal production when we put it out in the North Sea? Then after this, I will do a breakdown at component level to assess the component level of the costs, to assess scaling gaps and estimate what the levelized cost of energy would actually be if we put out the Crestwing device in the North Sea. And finally, what is the aim is to develop like a tool that will help advance the technology towards a more, you would say, techno-economic or yeah, better economic performance, better a lower price for generating the energy. And what I hope to do is to make this kind of model so it can be both be used by developers to apply into the development of the technology, but also something that is easy to disseminate and explain to stakeholders who should make decisions on, and investors that might be interested in how can we trust this technology. And hopefully also this could be something that is transferable, at least also to other kinds of wave energy converters, because the problem with the techno-economic efficiency is not just something that applies to raft wake. It's every kind of energy converter that struggles with this. I'm quite inspired by a system invented by a German researcher, Joachim Weber. I don't know if you know the technology readiness level. Yeah, that's something that says how ready for the market is the technology on a 1:9 scale. But he came up with an idea that instead of looking into how ready to market the technology is, then rather look into how well does it perform. And the levelized cost of energy is part of this technology performance level regime, but it's not the whole story. There, he also uses social acceptance and environmental impact. But the idea is to drive the energy towards better performance before advancing the technology readiness level, because when the further out the line of the readiness level, the more expensive it becomes to change anything in the design. So if we can keep the design as far as long as possible in this area here, in the low TRL level, while enhancing the performance, the better, because then we can end up with a readiness level that actually performs in a way that is competitive. But this is the TRL is an index regime, so it's a number, and therefore what I hope to do, I'm inspired by this way of looking at the technology to push the performance before the readiness level, but still what I want to do is to make like actual calculated estimates rather than an aggregated index, because then we will have the cost numbers and the actual cost of energy to look at, and that I think is more, say, relevant for pushing the technology into the commercial stage. Yeah, those were words.
Thank you. So that's time for a couple of questions. I think we need a microphone, do we? From the other Sandy in the room.
Yeah,
Taking so much time.
I'm not quite following the performance readiness level against the technology readiness level. It's not my question. My old boss used to tell me that TRL 1 to 3 was rocket science, which is the easy part. It's when it gets to 4 to 7 is rocket engineering, which is when you're building these things, and that's when they fail, and that's the hard part. So rocket science is simple. Rocket engineering is the hard part. I've got quite a lot on photovoltaics, and they've got a sort of energy efficiency that you can measure quite accurately. So when you're looking at something which has got light shining on it, you know how it's 20% efficient or 40% efficient or 41.3% efficient. You can measure that very accurately by looking at how much light is landing on it and how much energy you're taking off. Obviously, with these models, it's very hard to understand how much energy is coming off a buoy bouncing up and down against something that's flexing, because you don't know how much energy is going into the wave and what's coming off the wave through your machine. That's an interesting model to look at, and I think unless somebody does that model, how do you know a raft model is better than a buoy model? How much energy are you taking off out of a wave using a buoy against a raft? Because in the photovoltaic analogy, a silicon will take off up to 38% maximum of the energy of photon. A perovskite photovoltaic will take off 45% in theory. We know that, we can calculate that, but we don't know how much energy from a range of wave heights or wave lengths from a wave, a water wave. That would be an interesting thing to do that and compare that. You could take 5% energy off a raft wave or 20% off a raft wave. What is the maximum that you could take off those waves? That would be an interesting theory to do.
I mean, in controlled conditions, for the crestwing, at its peak efficiency, when it really hits the point, it can actually extract 80% of the energy that is in the wave. So basically, you have flat water when it has.
That's the perfect wave for the perfect machine.
Yes, in a perfect lap condition.
But again, over a 1,000, over what is likely to be the average waves over that length of time. The spectrum of a waves in the North Sea would be the efficiency of that rather than one single wave in one day.
What you don't know.
Yes, that's the interesting thing that I would like to see.
Yeah, and you can say on top of this efficiency, this hydrodynamic efficiency also comes the power takeoff, because the power takeoff is like it's a powertrain of different components and gears and I don't know, and a generator, and it doesn't have like a linear output that just fits what comes into it. It also has maybe like this peak curve. So you can see there are the hydrodynamic efficiency is only a fraction of the complexity of the raft WEC system until you have the actual output, because you have variations in the input from the uptake of energy, but then you have on top of that you have the PTO and generator that also has its own profile. So it's really difficult. There are a lot of different parameters and non-linearities in this area.
Nice.
Yeah, I agree that there's a lot of complexities in that, and I think you showed very well from a PhD point of view. It's a very rich area for development. One of the things that I was thinking about, as you showed at the early stages, a lot of the technologies that unfortunately are no longer with us because they didn't reach a commercially viable model. And I can see how the bottom-up approach was very well laid out in your presentation, the different elements, but as Sandy's saying, there's a lot of variability within that has to be dealt with. I also wonder whether there's merits in going to the end point, and all of these technologies in the end are trying to serve a market. And so you highlighted, for example, an offshore oil industry market, and that market is willing to pay a particular price for energy of a particular type. And working back from there and saying, well, if I need X megawatts to be delivered with this reliability and this consistency at this price, how does the WEC need to behave to deliver that?
Mm-hmm.
It's a slightly easier proposition because you can give an envelope of performance, but go into your performance level, and when that gives guidance to developers about where they need to be, it doesn't tell them how they need to get there, because the challenge from the bottom up is you have to choose something to get you to that answer.
Yeah.
So I do wonder about that. And yeah, maybe that's a simple enough proposition.
Yeah. But what also I think it bothers me a little bit is that wave energy converters, and right at this moment there are over 3,000 patents of wave energy converters around. So it's and some of them are there are a lot of different. They are fundamentally different work principles. So you cannot just compare them across and say, but this is a converged design, because also they are developed for specific places. They are developed either for the wave conditions at close to the shore or far to sea, or they sit in the shoreline, and all of them are sort of maximized or optimized to the specific conditions that they're working on. But what bothers me a little bit is that I don't know if it's harsh to say, but some of the developers cling a bit to this maximizing the energy absorption of this of the structure, rather than saying, okay, we try to optimize, we make a standard model and then look for the right places to put it, rather than locking yourself in and say, oh, but at this particular place, what do? We make it 190.7 meters long, and I mean, it's not a standard.
Yeah.
Mm.
And it will be expensive to custom make every single device. You would never be able to make arrays or wave parks, because if you need to make a new structure with different measures every time you make one, it's not going to live. So yeah.
Yeah.
I just have a quick follow-up, which is just on what Trina just said there, which was this may be one of the, in your 5 cost elements, one of the things I don't think was in there at the moment is the development cost of the technology. So what we've seen is, there's some machines that have taken 100 million pounds to build one machine, or it's taken 50 million pounds or 10 million pounds or
Yeah.
1 million pounds, and it depends on the size of energy you're going to get out of it.
Yeah.
But some machines that have quite a small energy output have cost an awful lot of money to produce.
Yeah.
And the first one isn't viable. And sometimes the industry says, oh, we need 10. Or some people might say we need 100. Some people might say we need 1,000.
Yeah.
Those 1,000 machines need to be paid for within the cost model that we're looking
Yeah.
at, because nobody else is going to pay for it. So I think that's really something that's worthwhile building in, is the development cost part of it as well.
That's also a reason why I chose, you would say, a modest approach to the levelized cost of energy, because I'm not going into any benchmarking against other technologies, because that wouldn't make sense, because the development costs in this area are so tremendous. So it's more like a measurement to indicate where is the technology itself. Is it on a good path, you could say? Yeah.
I'm just going to ask a quick question, because
Yeah.
it's the thing that's might be in other people's minds. And you kind of answered it partially, I think. But wind energy, we've had a fall in LC levelized cost. The cost of the wind energy has fallen by an order of magnitude and more. Photovoltaics, 2 orders of magnitude. The cost is 100th of what it was 20 years ago.
Yeah.
Why aren't we seeing that with wave?
I mean, in wind energy, you have a standardized technology, a well-known technology, and also wind energy was actually developed once, so it has been through all this. And wave energy has not overcome that initial stage. It's and also because the wave conditions are so different in different parts of the world, and it's where the locations where you really have high concentrations of wave energy are far out to sea. So it's just super difficult and super expensive to overcome that
Mhm.
that hill.
Okay, but the prize is big if we can do it. Okay,
Yeah.
thank you very much. Can
Thank you.
everybody just say thanks again? Thank you. Do you want to do a quick introduction there?
Thanks, Sandy. Yeah, this is like a Brucey bonus for ORF. My name's Gareth Davis. I'm one of the co-directors of ORF, and delighted that Klaus Espinal from the Lofoten Islands has come here to Orkney for the 3-day visit. And he's got a presentation, just 10 slides to kind of introduce the project, a little bit about the Lofoten Islands. You know, everybody from Orkney, I think, knows about Lofoten. Some of us have been lucky enough to get there. I think all of us would love to get there. And after you've seen Klaus's presentation, you'll definitely want to go there because he's got some tourist images in there as well as technical images. But just thought it was useful just to explain what's happening there. Lofoten is, as Klaus is going to explain, is really interested in what's happened in Orkney, the good, the bad, and the ugly. And I'll let him show us that in a bit more. We'll just get the technical changeover done.
All right. Hi. So thank you for the introduction and also for hosting my visit. As Gareth told, we're situated in Lofoten area. Our project is called the LOVE Renewable, or Love Renewable, if you like, where the LO stands for Lofoten and VE stands for Vestfold, which is the neighboring regions. So this project is actually owned by one of the municipalities in the region, and I work with Ega Utvikling, and we are the project managing team for this. We got some public funding to just kick off this project. So I come back to what the project is. First, I just want to give a short put you in the right spot in the world. I didn't circle in Norway on the global map. I just reckon you would figure approximately where that will be. So Lofoten and Vestfold is this region north, this archipelago coming out just above the Arctic Circle, which will be around here. So we're going into polar nights in 4 days, I believe. So I'm very glad to be here to gain some D vitamins while I can. And this is a image of the Lofoten and Vestfold region. It's a bit misleading because this is connected to mainline by road from here. So I just made a short hard cut at the border of the region. But still, as you can see, it's a very island community, and it also consists of quite some municipalities. I believe there are 11 of them. As for now, soon there will be fewer. And yeah, just to give you a glimpse of the season, this was the picture taken by me 10 days ago. So that's where we are right now. And this region has always been a fisherman region. Today, we are 60,000 inhabitants in the region as a whole. And for Northern Norway, this is a big region. It's scattered, so we don't have many big cities, but it's considered one of the most dense populated areas in Northern Norway. And this image is, of course, from back in the days. I believe this is by late 1800s, which they were able to fill in some colors. Or maybe, no, this must be later because we have motorboats. But this is what traditionally Lofoten looked like. Fishermen would come here to fish, every winter. We have the cod coming in to breed from the Barents Ocean, and this was the main breeding ground for the cod. Later years, we've had more aquaculture, and this represents kind of the new generation within aquaculture. This is a ocean farm. It's called. It's located in Vestfold, and of course, when you look at this massive structure, you also would possibly understand that the aquaculture also generates a whole lot of supporting businesses. So we do have industry, both land industry related to fishery, but also industry related to aquaculture, and that being everything from pumps to nets and pens and mooring, and yeah. So a lot of capabilities that are very relevant to the topics discussed in this room. Later years, tourism has become a very important driver for the economy in the region. And you would, if you Google Luften, you would probably find images looking like this. They're not lying, but but that's kind of where we're moving towards more and more tourism. And the power situation here is interesting because we do have some production. It's at about 280 gigawatt hours, but as you can see, the energy demand in the region is very much higher. We have 232 kilovolts lines coming in, and this is the most technical I will get during my presentation. Basically, we do have a bottleneck coming into the region. It's very hard to grid connect with more than 1 megawatt at the moment, which is a challenge because that limits also the green transition. It also limits establishment of new industry. So why are we starting a test center project in Vestfold? Well, this is one of the backgrounds. It's a part of the background that we have a huge we do not produce enough energy ourselves, and there's a high energy demand to both for existing industry to meet the green transition, but also for new industries to establish. So if, for instance, traditional fisheries are going to convert to electricity, which some already have, we do have charging for fisher boats. We will eventually need a whole lot of more power to host that. And also for the aquaculture industry, some of them are still running on diesel. That's also part because of the remoteness of the industry. But bringing them onto grid power would be it would demand even higher electricity demand in the region. So this is an issue for us locally. And the capacity, as I mentioned, very low. We recently had an instance of a industry, a feed for fish farming company. They wanted to establish themselves, but they had to find somewhere else to do that because they couldn't get the capacity. So we're actually losing opportunities as we speak. The production is very low, and there's almost no possibility to increase the hydropower production in the area. As we can see, we have very peaky mountains, and this is the ocean, meaning we have very few reservoirs. The water will just run into the ocean. So the beautiful nature, that's also a challenge for power production. There are also limited areas for land-based wind turbines, both because of the terrain. We have, yeah, as I mentioned, high mountains. We do, of course, have some flat areas, but we have a lot of bird life. We have also a lot of tourism that would be negative towards wind power. So this is also politically very controversial to talk about land-based wind. I'm sure there are some potential, and you could possibly find some places to put up some turbines, but it wouldn't, or it would be hard to kind of fill the total need with that alone. And we haven't seen any in the Lofoten region. We do have some in the Vestland region. So, but it's not a lot, but they do produce a substantial amount of the production in the total region. And as I mentioned, coming off the fishing and aquaculture industry, we do have a service and supplier industry. And also, if you zoom out at the uh, northern Norway region, we do also have some more offshore oriented supporting and supplier businesses. So we do have capabilities to build new industry. And we believe that this situation is also similar or at least transferable to other island communities, which is interesting to us. If we can be a part of the solution here or find a solution that could be transferable to others. On the upside, we do have good conditions for tidal. We do have quite some tidal streams. We do have winds, we do have wave. So the initial idea here was, okay, so let's make use of them. And what's also good is that we have a fairly good grid capacity within the region. So we do have bottlenecks coming into the region. Within the region, we have good transmission capacity. So summing up all of this, we kind of asked the question, wouldn't it be perfect for a test center for wave, tidal, and floating offshore wind? Yeah, we thought so, and so did the municipality of Hadsel, which then engaged on this project. So our mission is to try to establish a test center to shorten the road from pilot to market and bridging that gap. And being a municipality-driven project, we also hope to do this in dialogue with existing stakeholders. There's no secret that there are many interests in both the ocean when it comes to fishery, when it comes to aquaculture, but also when it comes to tourism and also the view, like the landscape. So we want to figure out if this is even possible. And the goal is to offer test areas within wave, tidal, and ocean wind. So what we did, or a colleague of mine, she started this project and she found Aquaterra. So so we built a consortia, which consists of Hadsel kommune, the municipality, that's the owner, Eiga Utvikling, which I'm representing, and also Aquaterra, Core Power Ocean might be a familiar name, as well as Flumil. Met Center is a testing center for offshore floating wind in Norway, and they are also part of the project. And then we have other local communities and power companies and grid owners. So the first step was to map the resources in the area, which we did at least last year, but the final results, I believe, came this year. And we have mapped out a couple of areas in the region. We found some promising wave power area. We have located a floating wind power area, potentially. This is very close to the ocean farm that I showed previous. And we do have identified 2 areas for tidal. One production area. It's bigger, deeper, more currents than this smaller one. So this is the one we're working with now. So where we are right now is that we're working to establish a shallow water tidal test site at this location together with Flumil, so they can test their horizontally mounted tidal turbine. And where we go next, that kind of depends on both the runway for this pilot, but also the market, really. We do see tidal coming up as maybe more ready to go to market than wave. So, but we are also looking into how we can engage within wind, offshore wind. So, I mean, that's why we're here. We're here to learn and get inspired by a community that really succeeded, I would say, in building test center facilities, engaging local community, engaging local businesses, and actually make both pathways for new technologies, but also maintain and build new jobs, which would be very interesting to learn from. So I believe also a shout out to NORA program that funded our visit. So yeah, thanks for being here. That's me.
Thanks so much. Very interesting. Anybody contribute? Any quick questions? Can you go on?
Just a quick one from me. What sort of tidal stream rates are you getting in your tidal in the tidal generating areas?
Yeah, so for this smaller one, oh, I can't really remember, but I think it's 4 meters per second. It's fairly shallow. It's 7 meters deep. But this device will only need to span, I believe it's 3 meters of the water column. So this is definitely a test site and not a production site because it's quite sheltered. But we do have enough currents that this will be an actual test site. When we look at the bigger ones, we have more up to 6 meters per second at peak, and deeper. They're more in the ballpark of 20 to 30 meters deep. And the strait is, even though it's trafficked by boat traffic, the strait is wide enough to be able to install some units without being in conflict. There's failed to mention, but there has already been one tidal test there previously, and there was also given consent to a second one that never happened. So we're trying also to build on those experiences previously from this region.
Thank you.
Okay, thank you very much. It's really interesting and lovely to have you here, and hopefully strengthen that existing, historic link that Orkney has with Norway and learn from each other. So thanks very much.
Yeah, definitely.
Okay, so that kind of draws the evening to a conclusion. Thanks to everybody for turning up, and if I don't see you again before Christmas, have a good Christmas. Thanks very much. Take care.